Annie. All right, we're going to start the last half of chapter 17, which is electrochem. So we will finish up everything we need to do this block. I'm going to go back to the slide before this, where we introduced the Nernst equation. So we know that if cell potential is related to a spontaneous reaction happening, then it must be related to somehow the quantities and delta G, because delta G tells us if a process is spontaneous, if it's negative, and Q relates a delta G for standard state conditions back to a delta G for any conditions that we happen to put into our system. So if we're building a battery, for example, our Q would have a certain value depending on the chemistry and the composition that we put into our battery for the chemistry. So we saw that the Nernst equation, because we know that delta G is equal to negative NFE, whether it's standard state or not standard state, we know we can take the top equation and combine those two and come up with the Nernst equation. So the Nernst equation is going to allow us to compare or relate the cell potential at any conditions to standard state by the Q, which is just the equilibrium expression, but not concentrations at equilibrium. So I recommended in my last lecture, use the middle equation the first time it's introduced. You can use these other two, but they're more specific. So the Nernst equation is just giving us some chemistry and asking us to calculate what's the potential. So we'll just put that into our Nernst equation. Q will be Cu2 plus over iron 2 plus. Oh, no. Cu2 plus times iron 2 plus divided by iron 3 plus. So that will be our Q value. I have to start out by getting the E standard, so the E0, and then putting the other concentrations into the Q, and then remembering it's negative. They're using the other form where the 0.0592 has replaced natural log with log. It's also replaced R with 8.314, and it's replaced the temperature with 298. So that equation can only be used at 298. So plug all those numbers into the Nernst equation and come up with a cell potential of 0.25 volts. So one of the things you've done this block is you've used a pH meter, and a pH meter is just an electrochemical cell that's sensitive. The voltage is sensitive to the pH. So I prefer, when you're thinking about using an electrochemical cell to determine pH, just go ahead and use the Nernst equation. Your book rederives an equation, but it's nothing new. It's just getting the pH directly in there because we know there's a log of a concentration or a pressure. So I prefer just use the Nernst equation and calculate the pH. Standard cell potentials and equilibrium constants. So just like we know the standard Gibbs free energy change is related to K by the right-hand equation on the top line. We also know, because delta G is related to an E0, that it must also be related to K. So if we set those two equal, you can derive an expression in the middle, which is the E0 equals RT over NF ln of K. You can replace ln with log and get the 2.303. You can replace the ln with log and R with its value and T with 298. And the bottom equation that they have in a box would only be valid at 298 or 25 degrees Celsius. This is just reminding us what we know about Ks, how they relate to if K is larger than 1, the reaction will go forward more than backwards. If it's less than 1, the opposite. So we now know 3 different ways to determine equilibrium constants, and I've mentioned a couple times that equilibrium constants, just from concentration data, which is number 1, are pretty hard to get accurate. So you have to be able to measure the concentrations somehow for each of your reactants and products, and that often is difficult, and you often don't get great values. The second way was with thermodynamic data. So that D in equation 2 here should be a delta. We know if we can get delta G standard state, we can get a K. That's much more accurate. And now we have a third way, which is from electrochemical data. So if we can get the cell potential under standard conditions, we can get a K. So 2 and 3 are pretty accurate ways to measure an equilibrium constant. So now we're going to move into thinking about specific examples of electrochemical cells. The first one, which you've all used in your life, is a lead storage battery. That's the battery that's in your car, unless you have an electric car. If you have a normal internal combustion car, you have a lead storage battery. They're heavy. The chemistry's toxic, lead. So they've caused a lot of deaths of animals and people just because you accidentally dispose of it wrong, and that lead gets out into the environment. They also have to be very acidic. So battery acid can burn you. So just a couple reasons why the chemistry is not ideal, but it's a very, very good rechargeable battery. So you can recharge it, which is another property of a battery that you have to consider. So the lead storage battery can be charged over and over and over again. And when we look at why, it's because the lead sulfate is a solid, so it's going to coat the electrodes. So if you put electricity in and try to force the reaction backwards, that lead solid is on the electrodes, and so the electricity can get to it, and you can force the chemistry backwards and start over again with a spontaneous reaction. The reason why in the end your car goes on bumpy roads and you travel with your car, and so there's just a lot of turbulence in your battery. So over time, if the lead sulfate, which is the product, breaks off and falls to the bottom of the battery, gets to the point where you can't recharge it. So there's a point where you have to get a new battery, but for a long time, it's a rechargeable battery. Another one is a dry cell battery. So these are not rechargeable. Just showing you the chemistry. So I wouldn't ask you to remember any of this chemistry, but just think about the important properties when you're picking out the chemistry. Cheap, abundant elements are the best. So like when we talk about our new lithium batteries, lithium is not abundant. It's hard to get, so it makes it expensive. So batteries that don't have toxic chemistry, batteries that use elements that are common and plentiful, batteries that allow you to recharge it, all of those things are super important. These are just a couple more. No, this is the same battery, but it's showing you the anode and the cathode. Yes. So it's showing you the chemistry at the anode and the cathode. Nickel cadmium batteries, you've used those, I'm sure. Nickel metal hydride batteries. Some of these are really nice because they're completely solid, and so the cell voltage stays constant, because we know solids don't go into Q. So essentially that says that the cell potential does not depend on how far the reaction is to completion. As soon as you run out of one of the reactants, it stops. But before that, it stays constant. So if you look at that bottom overall reaction, it's all solids. And if you put those into the Nernst equation, into Q, that would just be 1, and it would stay constant until the chemistry changed and there was one of the solids was gone. These are the lithium batteries. Nice thing about lithium batteries is that they're light. They do have an element that's mined and is not abundant, so that's a problem, but they allow us to use electric cars, because when you have an electric car, you don't want to be carrying really heavy batteries because that takes a lot of your electricity. So lithium batteries are good in that sense, and they're also good because they're rechargeable. Okay, so now there's another thing to think about, which is other ways that electrochemistry impacts our life, and maybe not always good. This is just showing you the chemistry of rusting, like on your car, so corrosion. And this shows you what's happening at the anode and the cathode. So you need to have oxygen present in order for this reaction to take place. So anybody who's from a state like Minnesota, where your cars would get rusty and start to fall apart, you need water, and you also need acid. So those two things have to be present. So prevention of corrosion, you can, for some metals, oxidation protects the metal. For other metals, there are two main techniques. Galvanizing it, so taking your iron and covering it with zinc. Zinc won't react in this reaction, so that's one way. And this is just showing you how that works. And then cathodic protection. So instead of coating the entire surface of the first metal with the second metal is placed in electrical contact with the first metal. And so that also can reroute essentially the electrochem to a different metal that won't impact the iron that makes up your car. So electrolysis and electrolytic cells. This is the last part of the chapter, and it's important. I mean, an electrolytic cell would be equivalent to your battery in your phone when you plug it into the wall, because you're forcing the reaction to go backwards to build up reactants again, so you'll have a spontaneous reaction. So a galvanic cell, the first one here, has a positive E and negative delta G. Electrolytic are non-spontaneous, and you're forcing them backwards. So the E is negative, the delta G is positive, and you're putting work in. And then when your battery's at equilibrium, it's dead. So you either have to force it backwards by recharging it or throw it away if it's not a rechargeable battery. So this is showing you a few different kinds of chemistry. So what we use electrolysis for. So we use electrolysis to make a lot of resources. So chlorine gas and sodium metal in their pure forms in this product are not the ways you'd find sodium and chlorine. So if you use electricity, you can force this non-spontaneous reaction between sodium plus and the chloride anion to make them into the neutral metal and gas, which are used for lots of things, chlorine especially, like for swimming pools. This is another one just showing you different chemistry for electrolysis to make chlorine gas. Electrolysis of water is a popular way to make hydrogen to run a hydrogen fuel cell. So you can take water and you can force it back into hydrogen gas and oxygen gas. This is another one. Sometimes you have to use liquid metals because water might interfere, so you can't always do aqueous solutions. So this is just another application. And this shows you oftentimes you don't use a salt bridge. Sometimes you use what's called a semi-permeable membrane. So if you put a membrane between the anode and the cathode, if only certain things can go through and the species that are taking place in the chemistry of the reaction can't pass through, you can keep the charge balance without having a salt bridge. There's another. Aluminum is one of the most energy intensive metals that we use. That's why recycling aluminum is so important, because if you start with aluminum oxide out of the earth, you have to add 3 electrons to each aluminum in order to make it into aluminum solid, because it's in the +3 state when you find it in a rock. And so in order to make new aluminum cans, you have to go through this process, which takes lots of electricity. Whereas if you recycle an aluminum can, all you have to do is melt the aluminum down and reshape it into another shape. And this is copper, same thing. You can use electrolysis to purify copper. And this is the quantitative aspect. So like I said, if you have aluminum 3+ and you're making it into aluminum solid, you're going to take a lot more electrons to do that. So this just gives you a flow chart for how you'd calculate a quantity. And we'll do some of these problems in class. So the current, which is in coulombs per second, times time will tell you the total amount of charge. And then the total amount of charge will be related to the moles of electrons by Faraday's constant. So if you're trying to make something like aluminum solid, you're going to take 3 moles of electrons for every 1 mole of aluminum solid. Other things like silver, it's a silver +1 that you'd be working with, and it would only take a mole of electrons. So this relationship will allow you to calculate exactly how much electricity you need. And that is the end of the chapter. We will work together on a lot of these problems